questions for Lab 2? Interesting question. One group found that when they had a note or two, how many notes? One note, 10, 25 notes? What was it?
11 by 11.
11 by 11. That you'd start out with a nice damp sine wave, and then at the end would be a non-vanishing, small, more or less square wave. And that's called a limit cycle, where the linear, the quantized differential equation is only a good approximation of the continuous equation if the variables are large compared to the quantization limit. And when you get down to the quantization limit, the system is nonlinear. It may oscillate forever, just depending on the details. Any other questions about week 1 checkoff? Oh, checkoff. The very first reading assignment, which is required, by the way, reading assignments are not optional, is the policy page, which outlines the grading policy. I didn't talk about this because I assumed you would read it on your own. But it became obvious on Friday that some people hadn't read that roughly 20% of your lab grade depends on the 2 weekly lab checkoff points. In other words, each checkpoint is worth 10 points of your lab grade. So these are not optional, you can't make them up, and you're graded on them. So you might want to read the rest of this. There's some information here on what kind of collaboration is allowed and not allowed between groups. And there's actually a summary of what the lab report should be, along with an example from a guy a few years ago who, what did we say? This report is typical of our best data. It's a good one. Don Beck was kind of overachiever. So, read the policy. Any questions about that? Any questions about grading policy? 10% for each of the 2 checkpoints, 30% for the project checkoff, 50% for the lab write-up. Any lingering questions on lab 1? I assume you probably, at least some of you, I know that at least 5 of you have bothered to look at the Piazza post from yesterday, which talked about some of the errors I saw on Friday. I can answer questions on that if anybody has questions. Otherwise, I want to start talking about generating repetitive structures. Any questions? Such a quiet. So, the Verilog includes a utility which allows you to generate Verilog from within the Verilog code. It's called a generate statement, and my favorite reference is this monster from Evans and Sutherland, which chapter 9, let's see if we have, there we go. Generate blocks. So a generate block is a block within which the statements should be interpreted as statements to generate Verilog. So the statements inside look a lot like Verilog, but it in fact generates Verilog. So generate blocks, are only defined and only produce any output at compile time, at system elaboration time, when you're actually building the circuit. This is a way of building a complicated repetitive circuit. Even though there's 4 loops in there, it is not iterative. It rather is a way to build circuitry. So any variable that you use in here has to be identified as a genvar, which can then be used to say the index of a for loop. I'll give you an example of this in a minute. Clearly, since this system is generated at compile time, none of the indices used can depend upon any computed data. This structure does not exist at runtime when you're actually when you're running the logic on the FPGA. It is only for elaborating logic, and therefore genvars have to be integers, and they have to be of fixed value. Or at least the endpoints of a loop have to be of fixed value. You can put a generate block into an always block. You can put a generate, in fact, inside any module. And items can include, of course, assignment. You can declare local temporary variables inside the gen block. You can produce if, then, else, and case statements in the gen block, which become conditional compiles. It says, build this hardware or build that hardware. It doesn't say anything about the data stream. It's which piece of hardware do you actually build if you have a choice between several pieces. So, in the case of the drum that you have to build, you might think that if you make one node, it would be nice to then stamp down 100 copies with a generate system, and you can do that. And that's what I'm talking about. As an example, any questions? Let's try to make it a little slightly more concrete by looking at an example of a shift register. So what we're going to do is we're going to define 8 D flip-flops. DFF means D flip-flop. And we're going to take a 1-bit signal, input to the first flip-flop, and shift it through the 8 flops to the output. And clearly we could do that. Well, first of all, we're going to define a D flop as having a clock in and out, and always at the pause edge, the out becomes the in. But to build the shift register, we're going to use a generate statement. And the structure of this is a little bit contrived. We're taking the clock and dividing it by some small amount to make a slower square wave to use as an input to the shift register. So path 0, which was the input to the shift register, is the 3rd bit, so of the clock. So count 3. And then we're going to define a genvar n that we're going to use as the index syntax for a for loop, we're going to step it from 0 to 7. We're going to name the for loop flops. It's a really good idea to name for loops here. Then we're going to instantiate the D flop of name U according to clock, using the first input as clock, the second one as path n, and the output as path n plus 1. So this is generating an array of wiring for you in a systematic fashion based upon an incremental description. These endpoints have to be fixed integers because you're generating real hardware. You can't generate fractional hardware, and you can't generate a variable amount of hardware. You have to do fixed hardware. It's named because you're making 8 copies of this D flip-flop, which are all called U here. But what's actually happening under the covers of the compiler is that U is being concatenated with the word flops and the index to make a unique instantiation name. So this name is concatenated with the index and is concatenated with the word flops. You get a unique identifier for that module. So 8 copies of this are going to be generated. And if you look through the net, there's a utility called the netlist viewer in Quartus that would allow you to, presumably, I haven't tried this, I should try this. You ought to be able to see the concatenated names of the modules on the netlist viewer. So you could imagine having, instead of the D flip-flop here, have your compute node and make a nested for loop. You can do that, 2-dimensional for loop, and step through and wire up an array of modules, of an array of compute nodes. Has anybody done this yet? This group has. Did you try it? Did you use Verilog or System Verilog? Okay.
We use System Verilog.
System Verilog is somewhat nicer in the way it handles arrays. There's also some interesting information. This site, Verilog Pro, which was active this morning, for all I know it's gone now. Oh, here it is. Has some interesting details about how the system actually works and what you can expect out of a generate loop, and what gets changed and what's constant. Naming conventions within generate loops and a few other things that I found interesting to read. You can't nest generates. A generate cannot contain a generate, but you can nest for loops within a generate. Yes.
Does the for loop have to go inside of a generate block?
Say again?
Does the for loop have to go inside of the generate block?
For loops are defined in Verilog without generate blocks, but it is much more controlled to use a generate block. For loops exist in Verilog without generate. Again, those are not sequential devices. They're not sequential constructs. They are a fabrication construct that allows you to make copies of hardware, not to iterate in time. So just like a conditional compile in C, this structure only exists while the compiler is working with your code. Well, Chorus is working with your code. It does not exist on the FPGA. So you're probably going to find that the compile takes a while. With the more hardware you put on, the longer the compile takes. One reason for that is that there's an elaboration step which is fairly quick, and then there's a placing step where the hardware has to be put onto the FPGA in such a way that it makes all of the timing deadlines. And I believe that the best algorithms right now are basically stochastic. You take a piece, you drop it onto the FPGA, you drop another piece next to it and ask if that meets timing. Then you put the next piece on, and you keep doing that until all the pieces are there. If it doesn't make timing, you wipe it and start over. It's NP hard. It is the knapsack problem, and so there's no shortcut. That means that as you add more pieces, it gets harder to fit them together.
Is there guaranteed to be a solution to it?
There is not guaranteed to be a solution. Particularly as the fill level of the FPGA goes up. That means that the compile times can become unbounded. Oh dear. Now, it's a little hard to tell that from some other errors that occur. For instance, combinatorial loops. If you take the output of a series of logic steps and feed it back into the input with no registering, with no timing, in other words, it's purely combinatorial, Quartus really has a difficult time trying to figure out what to do with it. To the point where the compiler may fail after 20 or 30 minutes. It's tediously long. This encourages you to look at the compile messages while it's compiling. You can do that. You can look at the warnings, you can look at the errors. You can ask, is something odd happening here? Or is it, does the compiler, does Quartus notice a combinatorial loop, for instance? You may want to do that. And of course, you always want to simulate before you put the system on the FPGA. You want to simulate the full-size drum with all of the features you need on it completely before you try and synthesize it, just for your efficiency's sake. Any questions? So how are you going to parallelize it? Make copies. For the 10 by 10, I think what the group did was to take one node and just stamp it down. Is that right? Make a 10 by 10 array of these guys, and done. And that works because probably every one of your modules had a multiplier, and there's 174 multipliers, 174 18 by 18 multipliers, And so there were no issues with resources. There was plenty of memory, plenty of multipliers. You just stamp it down. Once you get above 174, you no longer have hardware multipliers. So you need to figure out a way of reusing the multipliers. Or, of course, you could ask, how many logic elements does it take to make a multiplier? Because if you run out of multipliers, Quartus will just start using logic elements. And then the compile time goes way up. Because it's generating a tremendous amount of circuitry for a multiplier, for a fixed point multiplier. So how are you going to parallelize this? What are you going to do? What are your thoughts on this?
Take the multiplier out of the node and
Do what?
multiplex. Take the
Multiplex.
multiplier out of the node and multiplex it.
Multiplex the node. So you could have so as I talked about last time, you could take a group of 4 nodes, treat them as a sequential machine, compute this node, then this node, then this node, all using the same multiplier. And then after all 4 nodes are computed, at which time, by the way, the next stamp over would do the same thing, then communicate the results to the neighbors. So now there'd be a 2 states, there'd be several states in the state machine, which all of the nodes are following at the same time, which is to update the 4 internal nodes here, here, and every place else, and then turn on the communication, communicate nearest neighbor results, and then go on to the next time step and do it all again. Then you have to ask, what's the optimum size for the number of nodes that should be in a patch, in a serial patch? One node has 4 wires out. 4 nodes has 8 wires out. 4 by 4 array has 16 nodes and has 16 wires out. So the communication to compute ratio is getting lower and therefore probably better with more nodes per patch. So then you say, okay, what's the maximum number I can put in a patch? And that's determined by the length of the serial execution time that you have to run the internal update state machine. If you figure that it's going to take at least a cycle to do each node, probably more than that, probably 3 or 4 cycles, at least a cycle to do each node, then how many cycles do you have between audio samples? 20.8 microseconds. Are you running a clock 50 or clock 100? If you're running a clock 100, you have about 2,080 cycles to finish the calculation. If you're running a clock 50, you have half that. There's enough time to do quite a few updates. Now, are you going to use register memory? Are you going to use just general logic and store registers here? Because then you may run out of logic. If you start storing thousands of integers, you're going to start running out of logic because you can afford in ALMs, in advanced logic modules, you can afford to store something like 128 kilobits. So that's not much. That's only about 1,000 nodes. If you go to MLabs, the density is much better, and in fact, one MLab would do about 10 nodes in terms of memory. So, for any size parallel patch, you're going to have to ask yourself, how many operations does it take to do the serial evaluation of this patch? And that is going to be bounded by the time you have to do the update, which is 20.8 microseconds. You're going to have to ask yourself, how much storage does it take? Because sooner or later, if you use registers, you're going to run out of storage. If you use M10K blocks, you have 390 something of them. So you could make 390 parallel patches. So whatever system you start thinking about, consider total memory necessary, total time necessary, total number of multipliers necessary. You're going to be constrained by all three. Are there alternatives to, I mean, I'm drawing kind of a squarish looking patch here because that optimizes the communication, minimizes the communication relative to the compute. You have the fewest wires compared to the number of nodes with a square. Are there other possible shapes, though? What do you think? Any thoughts? One guy thought up a scheme a few years ago. I can't take credit for this, it was one of the students. And his solution was, let's make an array of compute elements which is hard coupled by communication in this direction, coupled to 0 on the outside edges. Those are the boundary conditions. So now we have like, it's a string, right? It's a one-dimensional wave structure. But what we're going to do then is cycle every row through that processor, every column through the processor. So this row represents all of the rows of the drum, but done sequentially. So then you have to ask, how much of a processor do you need? How much memory? How much sequencing? What other kinds of co-registers do you need for this compute element to operate? So what he did was to say, well, okay, let's assume that each of these compute elements has two M10K blocks on it. And this one represents U of n, and this of U n minus 1. Where, so we can read one of these at each time and feed them both into the compute module. Take the output of the compute module, feed it back into UN, and at the same time, forward this one to UN minus 1. But there's some details still to be worked out here. So we're going to make a sequential machine that spits values out of these two blocks, computes a new value, cycles it back into un, and copies un to un minus 1. So, what else do we need? Oh, there's all kinds of special cases. First of all, we have to maintain a separate register up here, which is going to take the last value of un for the current, that keeps un, the current un, for the row below. So if we have a 3 by 3 array, we feed this row in, and then to calculate this value, this node in the second row, we need that original value, not the updated value. So we have to keep for each row, we have to keep the initial value of the row above. So we need the above row, register above. Register below is going to be here. But for the top row, there is no register above because the value is 0. So the feedback from here is going to have to be through a mux, which chooses either 0 or the register above and feeds it back in. The register below value is going to be here, except when we're at the bottom row, and then we're going to feed a 0 in here because there is nothing below the bottom row for the nearest neighbor. So there's going to be a mux for the row above. There's going to be a mux for the row below. There's going to be a feedback from here to the M10K block, and from M10K to M10K U minus 1, N minus 1. And I think that's sufficient. So you're going to need to build a state machine then that cycles through something like 4 or 5 steps for each row. But during that 4 or 5 steps, all of the columns get computed at the same time. Because there's going to be 2 more memory blocks for this column and 2 more memory blocks for this column. So each column is going to have its own memory. All of them are accessed at the same time. So each column compute unit is going to execute a state machine that does a series of operations, which is going to be something like, I can write this out if you want, is something like read the top row, un minus 1, set this multiplexer to 0, compute the first value, and simultaneously shift the original, not the updated value, but the original value to here, back to here, and there's another step. You shift out the first value, then you set up M10K block for the second value to be output, second row, because you need the nearest neighbor below. The nearest neighbor above is going to be 0. The nearest neighbor below is going to be the second row, so you have to read the second row. Then you compute the first row. Then you shift the old first row up here, the new first row back to here, and the older value of un to the un minus 1. Then you repeat. Josh?
Can this give you like a 174 by 174 drum?
That is correct.
Max?
You can get up to about a 174 by 174 drum. There's just enough memory and enough multipliers to do this, so you can do something like 50,000 nodes. I'm not asking you to do that many nodes. But this is how the highest number of nodes has been done, is to hardwire a one-dimensional array and then shift the other dimension through the serial processors. So one axis is done in parallel, the other axis is done sequentially. Now, is anybody going to actually do this? Are you going to? Hold your hand if you're going to do this. Okay, so we've got the. So I guess I'm going to go through the detailed steps then. So, if we call this row 1, 2, and 3, then the steps are going to be something like step 1, read row 1 M10K to compute. At the same time, I think I called this mux B and this mux A. Set mux B to output 0. Actually, that's going to be step 2. Step 2, set mux B to output 0 and output row 2 M10K. This is UN. This is UN and UN minus 1. No, sorry. This is going to be UN n minus 1 here. So at that point then, you have all of the boundary conditions. You have the current value here. You have the lower boundary condition coming from here. You have the upper boundary condition coming from 0. Now in step 3, you can compute the new row 1. Then we need to shift old row 1 to the above register. Write the new row 1 to M10K while writing the old row 1 to M10K UN minus 1 UN. And then repeat. So now we're going to go back through, read row 2 to the M10K, from N10K to the compute, set the mux to, now so step 5 is read row 2 M10K UN minus 1. You got a question? No. Okay. To compute, set next is set mux B to above register and output row 3 from N10K U N. Seven is compute the new row 2. So you're going to go like this till you get to the bottom row, where mux A is now going to have to be set to 0 rather than the M10K because there is no row below the bottom row. And at that point, after you've done that step, then all of the values in the M10K blocks are the new values. So you're going to do these 3 steps for each row until you're done with all the rows. And at that point, the M10K blocks will contain the new step of the drum. Are you convinced? I see questions on people's faces, but I'm not sure quite what the questions are. Is it just that it's a big chunk to swallow at once? It's kind of some kind of really weird pipeline processor. You have a 2-step pipeline here, and the value here never goes anyplace. It just gets spit off the top and into the bit bucket, right? Because once you've used this value to compute this node, you don't need it anymore for the calculation. It's gone. So this is always the upper nearest neighbor, the upper nearest neighbor is either the row above or 0. This is always the lowest nearest neighbor, which is either the row below or 0. And the nearest neighbor calculations for the horizontal direction are carried out in parallel by connections, not in serial from memory. Still gonna do it? Yes.
So then once we've finished with the first row, we are just essentially looping 4 through 6?
Yeah, you're gonna be doing this over and over again. Right. You're gonna shift out one through 4. You're gonna do that over and over again. One for each row.
But we don't do 1 through 4 for each one, do we? Because that includes must be going to 0.
Oh no, in that case, right? That's only for the first row.
Okay.
And then for the bottom row, you're gonna have to switch mux A to 0 rather than read the output of row 2. A couple of groups a year implement this, maybe 3. It's a personality read. Who likes to do it which way? In some ways, this is more like a CPU design because you're you can think of this as designing a small instruction set for a small pipeline, where you're doing a couple of memory reads. You're then doing one of 3 or 4 operations: add, subtract, shift, multiply. And then loading a pipeline register, writing back to memory. So it's very CPU-like. But very stripped down. Probably not worth having an instruction set for, although you can imagine having another M10K block, which is an instruction store for your processor. Could you make that go fast enough? So for a 40 by 40 drum, you certainly have enough M10K blocks for 3 blocks per processor. And then you have to ask yourself, how many CPU clocks does it take for an instruction set architecture that looks like this to execute? And probably, it's probably 3 cycles per instruction or so. A fetch and execute, decode, execute. You can overlap them probably. You can probably pipeline those. But even if you didn't, if you just did a sequential processor, and it took even 5 cycles per instruction for 40 rows, that's still only 200 cycles, and you have 2,000 cycles. So the CPU, if you wrote a full CPU with instruction memory, fetch and execute, you'd still have plenty of time, because you're doing it 40-way parallel. All the CPUs are always running the same instruction. Right? So if you do 40 of these, they're all running the same instruction at the same moment, with the same fetch. Which means you only need one instruction counter and only one loop control. Josh?
Do you know of a way to like block this further, like do 5 rows at a time or something?
Oh, that's interesting. So, what if you did a not quite series parallel thing? So, what if you did What if you did 4 this way and 2 this way? And then calculated these all at the same time and then fed back these to the memory. So you could calculate 2 whole rows at a time rather than 1 row at a time. I don't see any particular problem with that. It's a little less regular, because now you have to sort of do different strategies depending whether the row is odd or even. But it should work.
Yeah, you mean 10 by 10 now. I mean, in the first case, first node. I mean, 10 by 10 node.
10 by 10 for checkpoint.
Yeah.
You're simulating a 10 by 10 for checkpoint 1, yes.
So that takes care of all the multipliers. So we can.
That you can do almost any way you want.
So if I make 16
That's
copies,
simulate only.
if I make 16 copies of this and time division that, then I can make 40 by 40. Okay. I have a 10 by 10.
If you have a 10 by 10 and you bolt 16 of those together,
Not bolting 16 of them together. I'm just reusing this at 16 different time points.
at 16 different time points. So the serial processor then is going to be a 10 by 10.
Yes.
So the memory that it requires is going to have to be 100 100 positions and 100 velocities. So 200 values, which will fit into two M10K blocks. So yes, it'll fit in terms of memory. It should also fit in terms of time, because you're now reading 200 values into memory, which takes 200 cycles. And you're reading them out again, which takes 200 cycles. So I think it, now, oh, but you have to do that 16 times. 16 times 200 is more than 2,000. So that won't work. Unless you're somehow using more distributed memory than just two M10K blocks. Maybe you could do it with, wonder if you could do, I don't know if you could do it with MLabs, which are denser than logic, but have more parallelism and not as dense as M10K blocks, but have more read-write parallelism. An M10K block will hold about 20 state variables, so that it'd be the memory for 10 nodes. And I don't remember how many let's just look. It's about 480 MLab blocks. Each holding 20 words of 32-bit data. So that's enough for 10 times, so 4,000 nodes. That's enough. That's 4,000 nodes worth of memory. And each MLab can be read and written at the same time. So that gives you enough memory bandwidth. And I have to think about how to organize that so that you could actually do that. I think you'd have to have 100 MLab blocks so that you could read all the nodes together and then bring them back out and read them for the next time step. That would probably work. Interesting idea. Yeah, good, cool. Different guy. Hopefully you have to sit over there. He's looking in there saying, there's nobody here. So, any other ideas for parallelism? I think that one would work. Relatively big blocks. Oh, we're past it. Oh, we need to quit. There's another time constraint. There's memory. There's time between samples. There's number of multipliers, and of course, not the least of the considerations is your time. Can you actually implement this in 2 weeks? Okay, thanks.